Pythagoras created over 25 proofs for the Pythagorean theorem. One of his mathematical ones is in the book. Aside from math, it is always helpful to allow students to see a visual solution to the same problem. The purpose of the video is to show that a squared plus b squared equals c squared using actual squares. To complete this project, each student will need the following supplies: one glue stick, one ruler, two 2-inch squares, two 3-inch squares, 2 sheets of copy paper, and 1 pair of scissors. To begin, grab some construction paper and head to the paper cutter. To make this activity fit on a regular sheet of paper, I made 2-inch squares and 3-inch squares. Make enough so that each student will get 2 of each size. You may wish to make larger squares that you can tape to your dry erase board to demonstrate the instructions to the students. Pass out the supplies to each student. Instruct the students to measure from the right side of the paper and make a mark that is 3 1/4 inches away from the side. Have them mark the paper in a different spot so that they can make a line by connecting the marks. Instruct the students to measure from the bottom and make a mark that is 2 1/4 inches away from the side. Have them mark the paper in a different area so that they can make a line by connecting the marks. From the intersection of these two lines, measure and mark 3 inches up and 2 inches to the left. Connect these points with a line. They now have a right triangle with legs 2 inches and 3 inches long, just like the squares you have handed out. Instruct the students to glue the 2-inch square along the 2-inch side and the 3-inch square along the 3-inch side. Instruct the students to set this paper aside and bring out their remaining sheet. Glue the 3-inch square in the corner and the 2-inch square next to it. This saves time in cutting away extra paper. Use the other 2-inch square to mark a length on the 3-inch square from the side opposite the 2-inch square glued next to it. Draw a line from this point to the corner on the 3-inch square and the corner on the 2-inch square so that the angle created by these two lines is a 90-degree angle. Cut out the 2 squares as a whole. Then cut along the lines. Do not cut the 2 squares apart. The students now have 3 pieces. Instruct them to observe the 3 pieces they cut out. They should notice that 2 of them are congruent triangles. Not only are they congruent triangles, but they also have legs that are 2 inches and 3 inches. Instruct them to form a new square by rearranging the pieces. What can they conclude? They can conclude using only the area addition postulate that the area of the small square plus the area of the large square equals the area of the largest square. While this is a fun exercise and it clearly proves the Pythagorean theorem, there is a question that we must answer. The question is, what is the significance of using the small square to mark a measurement on the large square? If you look at the large square, all we did was create the length of the triangle out of one of the sides. Since we used the 2-inch and 3-inch squares, we marked off 2 inches from the 3-inch side. The line drawn from corner to corner creates the right triangle from which the squares are based. When we glued the 2 squares together, the 2 lengths side by side created a segment that is 5 inches long. When we used the 2 inches to create one triangle, we were left with 3 inches. That and the 2-inch side of the small square created another triangle congruent to the first. But what of the weird shape that was created by cutting away the 2 congruent triangles? Ask the students to arrange the 2 congruent triangles on top of the shape. The only part that shouldn't be covered by the triangles is a small square. Ask the students to draw lines to mark where the triangles go, and then to cut out the new triangles. Ask them to set aside the little square for a second. We're now ready to prove another of Pythagoras' proofs of this theorem. Let's look at the triangles. They're congruent, so we really only have to look at one. This is a triangle with a 2-inch side and a 3-inch side. It has one right angle, so we know it's a right triangle. Now, if it had 4 right angles, it would be a square. It just so happens that we can make a square with the 4 triangles we have. We don't know what the measurement of the other 2 angles are, and frankly, I don't even care what they are. What I do know is that the measure of an exterior angle of a triangle equals the sums of the measures of the two remote interior angles. Since the exterior angle of the 90-degree angle is 90 degrees, then the sum of the two remote angles is also 90 degrees. I can create a 90-degree angle by placing the remote angles from two of the triangles together. I can create 4 of these angles by repeating the process. Hence, I have built a square. Check out the negative space in the middle. Our remaining square will fit in there nicely. Let's go a step further. What happens if I form rectangles from these triangles? If I place 2 triangles together, I get a rectangle. I'll do the same with the other 2 triangles. If I place them together like this, and I place my missing square in its obvious place, I am back to where I started. So in answer to the question, we found a way to assemble the 4 triangles and the little square into a square of the hypotenuse by using only 3 pieces, proving once again that the square of one leg plus the square of the second leg equals the square of the hypotenuse.